The goals of today's presentation are to discuss some of the features of Multi MEC and highlight the exciting new plugin integration with Abaqus CAE. I'll start by talking through what exactly Multi MEC is and why we think it's a critical tool in the tool belt of any composite engineer. I'll then walk through a few examples of our state-of-the-art composite virtual testing suite, and then dive into the Multi MEC for Abaqus plugin. If you have any questions during the webinar, please submit them in the question window. We will answer as time permits at the end of the webinar, and we'll send thorough written responses afterwards. If we can, let's start with a few brief poll questions so that we can gauge the audience and their experiences with composite analysis. Please answer the question as it pops up in your GoToMeeting application. First question is, what tool do you use most often for composite analysis? Great. Next, what's the biggest challenge with your current composite analysis technique? Great, thank you. So, Multi MEC in one sentence is a software offering a highly flexible bottom-up approach to composite engineering. The workflow involves generating finite element models of your material microstructures, virtually testing those models the same way you would virtually test a coupon in a lab, and then directly linking those models to the solution of a composite part. So on the surface, you may be thinking, this seems like a lot of additional overhead. Why should I care? Let's look at the underlying challenges in composites engineering, and that'll help explain why this approach is so worthwhile. It goes without saying that composites and the analysis of them is complex. There are infinite ways you can combine constituents to try and obtain the desired properties. There are also infinite ways that those combinations can then behave and fail. One can almost argue that there are as many design variables available at the microstructure level as there are at a part level. So it's hard to work with composites. But at the same time, reports show that about 70% of all product innovation uses some novel material with improved properties. So despite all the pain of working with these advanced materials, there is definitely a lot of gain. The question then becomes, how do you reduce the pain? How do you capture the behavior of both the part and the novel material efficiently and accurately without a supercomputer or your past experience to guide you? Many people, us at Multi Mechanics included, agree that performing a link between different spatial scales of your part, also known as multiscale analysis, is the wave of the future in composite engineering. Then the question becomes, well, how do you do that? How do you model the local scale and link it to the global? Many tools have gone about using an equation to try and govern that material behavior. However, just as there's no analytical solution to modeling the complexities and nuances of a part, like a fan blade, there's also no analytical solution to modeling the complexities of a material. At least none that we've seen. So how is it done at Multi Mechanics? We take a different approach. We've designed our tool from the ground up to have the flexibility to handle any new composite that may come about. Instead of spending time developing analytical equations, we have spent time developing world-class techniques for predicting composite microstructure behavior using finite element analysis, and then developing breakthrough algorithms to make an efficient link between that finite element local model and a finite element global model. It all starts with the generation of realistic composite microstructures. Multi MEC is able to automatically generate a wide array of composite microstructures in a matter of seconds based on simple geometric inputs. Also, we have spent a great deal of time finding ways to capture the complex mechanisms that contribute to composite material nonlinearity, and we make the assignment of those mechanisms as seamless as possible. Finally, we have an extremely unique approach to linking the different length scales without sacrificing accuracy or model fidelity. Let's look at a simple but powerful introductory example. Here we have fatigue on a multi-phase material. This beam is undergoing 3-point bending, and each cube is a representation of the material microstructure at different points within that beam. We load it with multiple cycles, and with every cycle, each microstructure evolves independently and starts to accumulate damage in different ways. Ones that develop damage are the ones that are loaded the most, as you would expect. And even though all microstructures were initially the same, they evolve independently, and that's just as it would happen in real life. Each part of your product experiences a different damage history. In the plots you can see the effect of this microstructure damage. At the top you see the displacement of the tip of the beam. With each cycle, that tip displacement is getting larger. The middle plot shows the stress of one of the elements. Stress is being relaxed over time because the resin is modeled as viscoelastic. The bottom plot shows the stiffness within one of the elements. That value is also decreasing over time because the element's stiffness is degrading as cracks evolve within the microstructure. So, as you load the beam, the microstructure is loaded as well, and the evolution of each microstructure impacts the global response of that beam. And that's true multiscale analysis. So a question we often get at this point is, where does one obtain the constituent properties for the material microstructure? To answer this, we teamed up with a few material suppliers to look at whether bulk datasheet properties of constituents can give a reasonable approximation of a composite material behavior. As you see, without any reverse engineering or coupon testing whatsoever, and using only simplified microstructure models, we were able to obtain properties within 10% of the experimentally obtained results in tension and compression along the fiber and transverse to it. We're also teaming up with material supplier SciTech to study the effect that local damage parameters have on the overall response of a composite. We found that if you ignore or improperly characterize the dominant damage mechanisms, your results can be significantly affected. It's this type of detailed modeling that other composite tools tend to gloss over or blur in their models. Here specifically we're looking at how the fiber matrix adhesion properties can greatly affect the overall composite response. One of the materials we work most frequently with is chopped fiber injection molded composites. Here you can see a graph capturing the stress-strain effects of the composite depending on different alignments and orientations within a chopped fiber part. In the images you can also see some of the different damage mechanisms at play within a chopped fiber composite. To capture the effects that fiber orientation have on injection molded parts, our tool integrates with injection mold simulation tools like MoldFlow and MoldX. Another quick example we've done is to examine the effects that voids or defects would have on the overall properties of a part. In this simplified model, you'll notice Multi MEC's proprietary crack insertion algorithm automatically propagating cracks throughout the RVE. Additionally, you see how the composite response is affected by the volume fraction of the voids. Finally, let's look quickly at woven composites, as those are becoming a very interesting topic for many engineers, and for that reason we've spent a good amount of time making it as easy as possible to generate any number of complex 2D and 3D composite weaves. Here you see our microstructure generation tool creating weave meshes on the fly. You can easily modify things like weave geometry, toe width, gap spacing, and mesh refinement, and generate meshes in a matter of seconds. Running virtual tests on these microstructures is just as simple. First, we define the geometry. We assign the material properties using orthotropic models for the toes and a viscoelastic resin. We're also using the automatic crack insertion algorithm to model debonding between the matrix and the toes. And we're using a stiffness reduction technique to capture rupture within the toes. We can homogenize the weave properties and see that anisotropy is captured. Finally, we kick off a virtual test. After a few minutes, we review our results. Here you see the weave and the stress response within one of its central nodes. You can see that as stress increases, toe ruptures begin to occur, and stress concentrations between the toe and matrix result in debonding. As that damage and debonding occur, the stress within the part is decreasing because the overall stiffness of the part is going down as damage accumulates. You can see the light green regions within that part represent the interface crack between the toe and the matrix. Eventually the part fails catastrophically. And you can see that the fiber and matrix are almost perfectly debonded in the toes along the path of tension. With all virtual tests, Multi MEC outputs a slew of data on the materials tested, just as you would get from testing in a lab. Also, to satisfy the request of some clients, we've developed a weave builder application to assist with the generation of complex three-dimensional weaves. Any weave imaginable can be generated using this great tool by modifying simple geometric inputs, and at the end we'll automatically create a finite element mesh. So in summary, Multi MEC's virtual testing tool is a great way to understand the behavior of your composite material, and if you desire, to optimize your material designs. But for most people, it's a means to an end. Once the microstructure is generated, it's time to link it to an actual part. For the past few years, this link has been done by combining Multi MEC's standalone, global, and local solvers. But due to numerous requests, we've finally decided to embed our breakthrough microstructure solution into an existing FEA solver, Abaqus. So a note on this integration is that we've not developed an analytical UMAT for composites. Instead, we've actually embedded a fully parallelized 3D finite element solver into Abaqus CAE. And to our knowledge, this is the first time this has ever been done. Hopefully from the earlier slides on composite variability, you understand why we went through all the trouble. So now let's take a look. To demonstrate the integration, we'll first look at a case study of a composite link made from long injection molded carbon fiber. As you see, we take an existing part within Abaqus, and when it comes time to assign a material, we point to one of the microstructures that was previously generated, or within the plugin you can create a new one on the spot. You use the plugin to generate an Abaqus material, and you assign that material to a section within your part. Easy. In this case, because this is an injection molded part, we also want to capture the variation due to the injection molding process. So we add the output from our MoldX simulation, and that automatically maps the fiber orientation onto the structure. You can see orientation varies significantly throughout the part, which is going to affect the overall properties. Finally, we execute the job and view the results in Abaqus. Here you can see that as damage accumulates within the local scale, the stiffness degradation gets passed up to the global and results in global part failure. It's clear when looking at SDV1 how the stiffness of the part degrades over time as damage accumulates. You can also display several microstructures from that part to see how they evolve over time. This is the true power of Multi MEC, in that you can zoom into your local scale to see where and why damage is occurring. Another example is with a woven composite on a plate with a hole. Here we'll demonstrate how quick and easy it is to swap different microstructures within an existing part. Here we have a 3D model with two layers, symmetric about X, Y, and Z. For the microstructure, let's start with a simple 2D weave like the one we virtually tested earlier. Let's take a quick look. Okay, we ensure that local damage is enabled, and we'll run a quick virtual test and see the homogenized properties. Next, we simply create a new job. We assign that weave to the entire part, and we're off. We can submit the job, come back a few minutes later to check out the results. We see that damage quickly propagates throughout the part. The damage at the local scale reduces the stiffness and causes catastrophic failure within that part. If you look at the stiffness matrix values that Multi MEC outputs, you can see how the stiffness in the part decreases as failure propagates. You can also look at the global reaction of the part in Abaqus. Finally, we can launch the viewer of our microstructures to see how they have evolved over time. And you can see that depending on where that microstructure was pulled from, it has a completely different stress contour and a different response as it's loaded. Let's say now we want to see how the part will behave if we add a hollow foam core of some sort. So we create a simple 3D microstructure with some voids. We add some crack and damage mechanisms to it. And now we'll perform a quick virtual test to see how the curve of that material looks. The virtual test takes about 50 seconds to run. We output the microstructure, and we can view a plot of the stress strain response within that material. And we can see it's stiff initially and abruptly fails. Not ideal, but that's okay. Let's add it and see what happens. So we create a new material, and we reassign the section properties of the plate. We give one layer the woven material we already created, and we assign the bottom layer to that new foam. Now we submit the job and check out the results. So as expected, the upper layer carries most of the load within the part. The bottom layer is relatively unstressed because it fails so abruptly. You can hardly even see it, but if you look at the stiffness components that are output by Multi MEC, you can see it starts with an intermediate stiffness and then quickly fails throughout. That causes the upper layer to carry the load, and then failure starts to propagate throughout that top layer. Interesting. Now let's see what the microstructures look like. Selecting from a few different elements within the part, we can launch the microstructure viewers. And as expected, the stress contours and damage mechanisms are different depending on the microstructure and where it is within the actual part. Same as before, you can also generate the reaction force of the plate and see how that load evolves over time. You see there's gradual stiffness reduction and then abrupt failure. A truly nonlinear response, and something that would be very difficult to obtain using most analytical methods. So using this process, you can imagine how easy it would be to test different varieties of composites in your part. Testing orientations, testing combinations, optimizing your material, and quickly seeing the response. That is the beauty and the power of Multi MEC's true multi-scale technology. The key to our solution is the modeling flexibility and speed that it affords engineers. Unlike most composite analysis tools, Multi MEC does not confine you to certain materials or periodic microstructure geometries. And since our solution is based on FEA and not based on an underlying analytical technique, your model doesn't have to become void when some arbitrary bounding assumption is broken. In this demo, we specifically focused on static analysis with Multi MEC and Abaqus implicit. We also offer similar multi-scale static analysis tools within ANSYS Mechanical. In addition, we support dynamic multi-scale simulations through our standalone offering and are developing similar integrations with LS-DYNA and Abaqus Explicit. So before we answer questions, we have a few more poll questions for the audience. 1. How would you rate this webinar? Next, what is your biggest barrier to using a multiscale modeling tool? Finally, what computational resources are available to you for modeling and simulation?